Let's start our conversation today about transition metals and how we can name them. Yesterday we talked about ionic bonding. Today we're going to continue that conversation. We're going to talk about transition metals, the ones that we find here in the D block. So we're going to talk about our transition metals and how they participate in ionic bonding. They do participate in ionic bonding because they are still a metal bonding with a nonmetal. All right, and so they still participate in that. Here's the interesting thing about transition metals. Because they're in the D block, and they're in the D suborbital, the D sublevel is filling, it will sometimes fill a little bit strangely in ways that actually allow these to have multiple oxidation numbers. The oxidation number is that charge number that happens at the top. So if it's in group 1A, we know that it's going to lose an electron and it's going to be a +1. If it's in group 2A, we know it's going to lose 2 electrons, it's going to be a +2. Those are its oxidation numbers. +3, plus or -4 if it, depending on how it oxidizes, -3, -2, -1, and of course the transition metals are inert and do not participate. So there's our oxidation numbers, and those for our representative metals, or the ones that are not in the transition or in the lanthanide and actinides, those are set, and so that's what you can expect. Within the transition metals, iron, for example, sometimes oxidizes as a +2, but also sometimes turns into a +3. And it depends on, it doesn't even just depend on what it's bonding with, it depends on which form of the element you have. And so it can oxidize into more than one number. Copper, same way. Nickel, same way. And so a lot of the transition metals actually have more than one oxidation number. And so then the question is, Mr. Willis, how can we know which oxidation number it is? I am so glad you've asked. And that is where we are going to use our Roman numerals. I actually had forgotten that before we get to the nomenclature of the transition metals, I wanted us to talk just for a second about some characteristics of ionic compounds and some characteristics of covalent compounds, which are going to be the molecular that we talk about today. These are opposites, but I do want you to record them for your notes. Ionic compounds tend to be brittle. They do not tend to bend or flex. They tend to stay until they snap and tend to fracture. Let's see. They have a very high melting point, like sometimes over 1,000 degrees Celsius. Okay. And they are electrolytic. What does electrolytic mean? If it's dissolved in water, it will conduct electricity. So if it's dissolved in water, it will conduct electricity. Yeah, Earth is kind of close. I saw a trick that another teacher did today. I want to see if, nope, I can't. Oh well. All right, let's see. There we go. And so it will conduct electricity if it's dissolved in water. If it's a covalent compound, it's less brittle, meaning it's more malleable, okay, more likely to bend or flex. It has a relatively low melting point. That doesn't necessarily mean that it's low, but it's much lower than your ionic compounds. It might just be a couple of 100 degrees Celsius. And you're like, how is that low? Well, when you compare it to 1,800, 200 is low. All right? And they tend to be non-electrolytic, meaning that they will not conduct electricity when and if they dissolve in water. All right, so that is that. So let us take a look at. Do we get those? Feeling good about that? All right. So let's take a look at how we're going to name transition metals. This is all information that's going to be very similar to what I had just said. The transition metals can have more than one charge. How do you know? And this happens because they can lose different numbers of electrons at different times. And so you have to specify which charge, specify meaning specifically say which charge the transition metal has by using a Roman numeral. Remember, our Roman numerals are things like this, Roman numeral 2, okay, or Roman numeral 4. I've always wondered if Roman paramedics referred to IVs as 4s. And so you can use that in the naming of your transition metal, in the naming of the compound. All right, so that is going to tell us the oxidation number, which also then ends up being the charge on the transition metal. So copper 2 ends up being a Cu with a 2 plus. All right. And again, there's not much to add to that from our notes yesterday. It'll interact the same way. We'll write that, for example, if copper is going to, if it's copper 2, then it would be Cu plus 2. And then if I have chlorine, which is a negative 1, I would just crisscross those up and get copper chloride with the 2 down there for the chlorine. All right. Do not use Roman numerals with the following. Group 3B. Find group 3B. If it's a B, it's going to be a transition metal. So find group 3B and tell me where it is. It's actually the first column of the transition metals. The first period, the first family or the first group of the transition metals. And all of those will have a plus 3 charge. Hey, 3B plus 3. That is not something that you can count on for all of them, though, so don't get used to that little help. Group 2B is always plus 2. Where's 2B?
Starts with zinc.
Yeah, you're thinking to yourself, hey, it's right next to 3B, but it's not. It's on the complete opposite end of the transition metals. And so it starts with zinc. We've got zinc, cadmium, and mercury, and they are all going to be a plus 2. Silver is always a plus 1. All right, so just get used to silver being a plus 1. And then other than that, you will have to look for the Roman numeral. The back of your periodic table actually has several common oxidation numbers for transition metals that we will frequently use.
Where is that? On which one? On which paper?
Oh, on the back of your periodic table. Just below the polyatomic ions, it's got several of your transition metals. All right, let's see. The other thing to say, okay, so copper 2 sulfate. Again, we know that copper 2 is going to be a plus 2. We find sulfate on the back of your periodic chart. And you see that it's an SO4 minus 2. Plus 2 minus 2, the perfect match. So we do not, in fact, put a 2 on both. It ends up reducing to be 1 of each. So copper sulfate, or you would say copper 2 sulfate. And nickel 3 chloride, it's-
How would you say copper 2 sulfate?
because it is the +2 oxidation number of copper.
So when we name it, we have to put the known flow.
Yeah, you have got to put the number there, because copper can be a +2. Like you can have copper 2 chloride, and you can also have copper 3 chloride. And I'll show you how you'll know in just a second. Okay? Yes, ma'am.
So far, anytime there's been the remedy, now it's been positive, how will we know that it's been negative?
It's not, because it will always be positive because it's the cation. Okay? It's our metal cation. So that will be how you'll know.
Say it says to write the compound out. How would you know it's
I'm glad that you've asked. Let's take a look at that. Okay. First of all, let's see. I'll show you once again nickel 3. So when we have nickel 3, then we know it's a +3. Chloride, chlorine, again, is going to be a -1. And then we crisscross those up to get nickel chloride with NiCl3. All right. Now here's what Hannah was asking about. What if we start with the formula and we go the other way? Okay. So Hannah, we're going to look at Mn. All right. What is that?
Manganese.
Okay, good, manganese. And you're thinking to yourself, what is the charge on it? Well, look at the subscript from the chlorine, or from the anion that it's with. Okay, so in this case, manganese, and it's got that 5 down there, meaning that we had 5 chlorines. And so that means that this had a +5 charge. So if I took this apart, so to speak, there's a 1 here, there's a 5 here, and so the original ions would have been Mn +5 and Cl -1, and then I would have crossed them up to get MnCl5. And so since I know that that's a +5, then I'm going to write manganese 5 and put that Roman numeral right there. Okay? Feel good about that? Feel good enough to look at another example? Okay.
But could you just always look at the anion subscript, or is that you get it?
Well, I'm glad that you've asked. Can we always just look at the anion subscript? And the answer is no. Okay, we'll come back to that here in a second on our third example. So let's look at this one. I've got 3 irons. I've got 2 phosphates. If we uncross that, we see that phosphate's charge should be PO4 with a -3. And so that makes sense. And then iron would have a 2. So it would be iron 2 phosphate. And again, our original, if we just uncrossed these, would have been Fe +2 and PO4 -3. All right, and so that's where we would have come from. Hey, now, let's say that you can't see this because you've been told to take this and name it. Okay? And you say, oh, look at that, I'm just going to uncross it. And it's going to be lead 2, and then sulfate with a -1. However, when you check your polyatomic ions on the back, don't write that. When you check your polyatomics on the back, is sulfate a -1? No, it's not. It's a -2, which means that since there were 2 leads and 1 sulfate, that you actually had, and this should be a -2, that means if you had 2 -2s, this actually had to be a +4. Okay?
That just
Okay.
Yeah, can we go back to the iron one? Because I'm not understanding.
Okay.
I understand the iron one. I don't understand the last one.
All right. So first of all, let's go back to iron. And again, you can't necessarily see this. This is what you've been asked to produce, this name. Okay? So let me just real quick, let me just hit all this and get that out of the way. All right. All right. So when we look at the iron, we say, hey, there are three iron compounds, or excuse me, 3 iron atoms. So iron, iron, iron. There you go. And then I've got 2 phosphates.
So why don't they just have the 2 in the parentheses next to the B?
Because these are actually interacting as a group, and so it's not just 2 phosphorus and 8 oxygen, it's 2 PO4 groups. They are a team, and they are winning and losing and interacting and moving and bonding and unbonding as a group.
Okay.
And so that is why.
So when you wrote it with the compound, or I'm sorry, not the compound, but earlier when you're doing like the switching, that 4 is there just because that's where it is in the compound, right?
Yeah, because there's 4 oxygens that are a part of that
Okay.
polyatomic ion.
Okay, that's
Now, on the back, I want you to find phosphate. We don't know the charge for iron, but we know that there were 3 of them. Okay? Phosphate happens to be a -3. So what's my total negative charge? -6. That means over here I have to have a +6 to have balanced this out in terms of my electron donor and my electron acceptor. All right? Since I have 3 iron atoms to total +6, they must be +2 each, which means that I have iron 2 phosphate. All right? And if I erase this and reveal my little answer, it is in fact iron 2 phosphate. Now, the other way you could do that is just by uncrossing your subscripts, and you say, oh look, it's iron 2, because it's going to be a +2, and my PO4 is going to be a -3.
But that's not a safe way.
That's not always the safe way. You'll get a feel for it. But the reason we say that that's not a safe way is because of our next one. Okay, so Hannah, let's work our next one the same way that we did our first one. Okay, so let me clear this. All right, here's the deal. So PbSO4, and then there's 2 of them. All right. So I need, let me roll that down just, whoop, there we go. So I've got 1 lead atom. There it is, Pb. I've got 2 sulfate atoms, SO4, SO4. Now, look on the back of your periodic chart and tell me what the charge is for sulfate. Look in the back of your periodic chart.
-2.
Oh, wait. These are -2 each, which means that my total charge is -4. I only have 1 of these. If I've got a -4 here, I need a +4 here, which means this must be lead 4 with its oxidation number of 4. Now, Hannah, if you had just tried to uncross these, you would have said, oh, lead 2, and then had, the sulfate with the -1 charge. But something in your brain's telling you sulfate doesn't have a -1 charge, and so you check, and you're like, sure enough, it's -2. And so you say, hey, I've got a pair of -2s. That means I had 4. I needed to accept 4 electrons.
But you would have known that lead doesn't have it's 4. It's charged 4, right? You would have known that.
Well, Now, if you look up there, what makes you say that? All right, and here's what I'll tell you. Let's see. Let me find that. Oh, I'm not. Where is lead? What number is it?
Group 4A, last one.
That's what I say.
Oh, okay. I see what you're saying. Group 4A. Yeah, and again that's fine because it's not a transition metal. But it's one that is that likes to share a lot of the times. Not in this case though. All right. How we feel about those things?
So it's just safe to write it out every time.
I wouldn't do that on the test because you're going to guarantee to get it right.
Yeah, if you write that out, you can always do that, and it's not going to hurt you. You know, it just takes a little time. You will eventually, though. It's kind of like in algebra where you started off actually writing. You know, if we had a +4 over here, you would write -4 on both sides. You don't do that anymore. You know, you've kind of moved past. And yes, some of you are like, well, I do, and that's fine. But some of us don't, and that's okay. You will get comfortable doing that or not, and I want you to do it the way that you're comfortable. Okay? If you do not know what your Roman numerals are, there they are. 1, 2, 3, 4, 5, 6. Anybody need to write down their Roman numerals? If you do, let's write them down. All right, so we're good. Great. Let's move on. Let's go to covalent bonding. Now, covalent bonding, which is also called molecular bonding or molecular compounds, is where you have a nonmetal and a nonmetal. Okay? So two nonmetals, that I know that says a no metal. It should say a nonmetal. So it's where you have two compounds, two nonmetal atoms that are bonding together. A covalent bond is where, remember that we talked about with our ions, when we talked about with our ions that electrons are transferred, between one and the other. In this case, they're not transferred. There's not enough grab and pull from one atom to fully transfer, and so they're shared, and so they end up sharing with each other. Okay. For example, let's see. Let's just look at carbon. Carbon is. I'll tell you what. We'll come back to that in a second. They all end in "ide" because they are all going to be binary, and we will use prefixes in the names unless it's a 1 at the beginning. Okay. But if it's any other number at the beginning, and no matter what the number is for the second, for the anion, you will use a numerical prefix to tell how many atoms of each one. We're not going to use charges, and we're not going to cross the subscripts because that does not work for us, or not necessarily. And molecular compounds are never reduced. Meaning, yeah. All right, so let's see. Which chart? The prefixes?
Yes, sir.
Yeah, copy those prefixes. You need to know those.
So like with the prefixes, so like it would be working on like number 7 is try.
So let's look at number 7's a great one. It says sulfur does it say triiodide or trioxide? Triiodide. All right, and so you look at the tri, and that tells you that there will be 3 iodides. Oh, we're not going to worry about that IDE. So iode So that's going to be iodine. So we're going to have I3 as the back part of that, and the first part will be sulfur. So there's sulfur triiodide. Why did we not say monosulfur or monsulfur? Because if it's only one and it's for the first one, you don't do that. If it's for the second one, you do. For example, if I've got a compound that is named, let's switch colors. If I've got a compound that is named dihydrogen, no, monoxide. Okay, in that case, since the anion, well, it's not appropriate to say cation or anion, but since the second part of the name does have only one, but it's the second part, we do put that MON. And since it's a vowel, we can drop the extra O. You don't say monooxide, you just say monoxide. Okay, so dihydrogen monoxide, what's that?
Two hydrogens and one
Five.
Water.
Yeah, that is the technical term for water. If you Google dihydrogen monoxide, you will find all kinds of funny little internet jokes, like about that dihydrogen monoxide should be banned because hundreds of people die from it every year. People talk about dihydrogen monoxide poisoning. If you get it in your lungs, it'll kill you, and things like that, like drowning. And
That's all my mom
and so you will, but then you'll also have people who are like, dihydrogen monoxide is essential for life. If you're deprived of it for more than just a couple of days, you die. And so you will, if you Google dihydrogen monoxide, you will find no shortage of internet shenanigans. Let's see. Hey, what about carbon monoxide?
Carbon, one carbon and one.
One carbon, one oxygen. What about 15? Okay. What about carbon dioxide?
One carbon and two oxygens.
Yeah, one carbon and two oxygens. All right? And so that is the way that we do that. Let's see if this last, look, some examples. Yeah, so carbon dioxide, carbon monoxide, dinitrogen pentaoxide, dinitrogen pentaoxide, dicarbon tetrafluoride, okay, diphosphorus, okay, meaning two phosphorus, pentaselenide, nitrogen trioxide, triarsenic nonafluoride. I always love the nana prefix for 9. Try to find a way to work. You know how if something multiplies by 2, we say it doubles, 3 triples, 4 quadruples. Try to find a way to work the word non-tuples into conversation today. Okay, meaning that it multiplies by 9. So, meaning, and I doubt that you're going to find someone who has non-tuplets. So there's not really, but try to find a way to work the word non-tuples, meaning multiplies by 9, into your vocabulary and into your conversation today. All right. Let's see. All right. So real quick, last one that I'm gonna do for us: diarsenic.
Arsenic? Like on the back?
Arsenic is poisonous. Trisulfide. That's number 15. All right. So that means that we're going to have
2 arsenic
2 arsenic
and 3 sulfide.
and 3 sulfur.
Sulfur.
Okay. There you go. Now, if I were just looking at this, what if I were given this? Then again, you would look and you would say, oh, look, it's a metalloid and a non-metal. And so that's going to be di-arsenic trisulfide. Yes?
Arsenic is AS.
That's our one.
Oh, thank you. Yeah, thank you. And I actually looked at the AS on the block, but that's not what I wrote. Thank you. Hey, what else? Anything else?
Okay.
All right. I think that we